All right, welcome back. So finally, we are going to do some calculus in Calc 3. We've gone through an entire chapter where we've just been going over the basics of vectors and the basics of surfaces in space. But now, what we want to do is since we have this new function, this vector valued function that we were talking about in the last video, we now want to see what we can do with it, right? What can we do with this new function? So go back in time. And when you first started your Calc 1 classes, your professor would have began with limits. And let's make sure you understand that your derivatives don't exist without limits. All of those recipes that you have memorized and learned, all of them are based on the idea of a limit. So we're going to go through limits quickly. I'm more interested in just a few key concepts, and then we'll come back to some of these things when we need them. Ready? So one of the things that I'm interested in is that you understand the idea of continuity. So what do I mean, continuity? So let's start with just a function. So to say, so let me draw a curve here. So to say that the following curve, the following function is continuous, let's start with a real informal definition. We could simply state that you can draw your curve without ever lifting your pen. Okay, so that's a good working definition. Later in your math career, probably sometime in high school, they would have refined that you can draw it without lifting your pen. They would have refined it by making a statement or statements like the graph has no holes in it, or the graph has no breaks in it. And then it's only when you get to calculus that we refine these ideas of holes in the graph or breaks a little bit further. So, but let's start. Let's start with just the easy one. So the idea is x is approaching c, right? So notice that here I've highlighted there's some particular x value, right? All of these are x values. We're interested in this one particular x value, and it's special enough that we'll call it c. And the idea is x is approaching c. So let's start if there's a hole. Obviously, so if I have a hole in the graph at C, well, that's problematic in terms of continuity, right? We would say that there's a discontinuity at a point, that point being C. Now, formally, the way you would say there's no holes in the graph would be to say that f of c. Now I'm gonna write exists right here in just a second, but do you understand what I have now? I don't know what this function is. I don't know what f of x is, but whatever it is, if I plug c in that function, it's undefined. Right? F, as of right now, f of c is undefined because there's a hole in that graph. But assuming there's no holes, then f of c exists. Okay, so the next idea of continuity is to talk about there are no breaks in the graph. So let me erase this and let's draw a graph that has some type of break in it. Well, let's just assume that it's a vertical asymptote. So maybe your function looks something like this. Now, clearly, this function is not continuous. We have a point of discontinuity. And you can't draw it without lifting your pen. But how do I how do I formalize the statement that there are no breaks in the graph, right? No vertical asymptotes like this. Well, recall the idea, let me erase this for a second. Recall the idea of a limit. And the idea is that as x approaches c from the left and as x approaches c from the right, your graph is approaching L. So, in other words, if there's no breaks in the graph, then the limit should exist. So we can say that the limit as x approaches c exists. And finally, if we just put these two concepts together, that the point exists at C and the limit exists as you approach C. If you couple these two together with the statement that the limit, I'll write it for you, with the statement the limit as x approaches C actually equals f of c. If you meet this criteria, then you have continuity at that point. If there's any point on your curve, right, you draw a graph, if there's any point on that graph that doesn't meet this criteria, then we would have discontinuity. Now you understand continuity and discontinuity. Let's go back to vector valued functions. So the ideas from Calc 1 apply. We basically make the statement, I can make this easy. For your vector valued function, r of t, if all the components are continuous at a point, then r of t is continuous at a point. Let's jump into an example. So example 5 says, discuss the continuity of the following vector valued function. And we are interested in what's happening when t is equal to 0. Ready? So what's going to happen right now is I'm going to take the limit as t approaches 0 of this function. I want to see what happens. So let's take the limit as t approaches 0 of r of t. And the good news is we're just going to take the limit component by component. So let's take the limit as t approaches 0 of t, and we'll do the same thing with the j component and the k component. So bear with me, let me write it. So limit x, no, not x, we're doing t. T approaches 0 of a, and I got one more. The limit as t approaches 0 of a squared minus t squared. Okay, so let's go ahead and evaluate this component by component. So starting with the I component, very simple. You remember that the rule that allows us to simply substitute, right? So that is going to be 0i. If I plug 0 in for t, I have 0i. All right, in this case, a just represents some arbitrary constant. And as you recall, the limit of a constant is just a constant. right? So the limit has no bearing on the constant itself. So as t approaches 0 of a, well, you just have a. All right, we've done the I component, j component. Now let's just do the final component, the k component. So limit as t approaches 0 of a squared minus t squared. We'll plug the 0 in for the t, and all we will be left with is a squared. So what you have here is the limit as t approaches 0 of r of t. So let's go back to the question. The question was, discuss the continuity of the vector valued function at t is equal to 0. So now we're here. We've evaluated the limit. Are there any problems? Did we run into any problems? No. I mean, we didn't run into any scenarios where we were dividing by 0 or square roots of negative numbers. None of that sort. So, in fact, r of 0 is simply equal to the vector a j plus a squared k. Fully continuous throughout the entirety of its domain. So no points of discontinuity. All right, so let's do one more with limits, and then we'll move on to building a derivative. Okay. So next question, it says determine. Now we want to determine the interval or intervals on which the following vector valued function is continuous. So let's note the question. The question is, where is it continuous? So let's start by figuring out where it is not continuous. All right, let's look at each component. So we'll start with the x component. F of t is equal to t. Then we'll do the g component, the square root of t plus 1. And finally, the h component, which is just t squared plus 1. All right, let's do this component by component. Ready? Start with f of t. Are there any domain restrictions on t? No. T exists from negative infinity to positive infinity. Let's actually jump to h really quickly. Are there any domain restrictions on h? Again, no. You can plug any t value that you'd like. G, there is a domain restriction, right? So for G, you can only choose t values that are greater than or equal to negative 1. All right, so this is, these are the domain restrictions component by component. Let's now remember what I said earlier, that the domain of your function r of t is always the intersection of those components. So in this case, we can simply go with t has to be greater than or equal to negative 1. So r of t, let's make a statement, is continuous from what? Well, t has to be greater than or equal to negative 1. So if we start from negative 1 and then proceed to everything greater than or negative 1, this would be the points of continuity. Continuous everywhere from -1 to infinity. All right. So we've discussed continuity, the ideas of limits for continuity. Now we need to use some basic ideas of limits to build a derivative. So back to this graph, right? So again, just for some context, you can see we have this curve being traced out. We'll stay in a plane. We'll just say in 2 dimensions to make things easy. And let's go ahead and, just for some context, let's assume that, I don't know, maybe this is some type of particle. You're the path of a particle, or the path of a comet, path of a meteor, and you're looking through your telescope at night trying to chart its movement, right? Okay, so let's label some things. So we know C is just the curve. That's our, the path of our particle. O is the origin. How would we think about point P? Well, let me see if you agree with this. So point P, so this is a point on the curve at time t. All right? So let's say tonight you look through your telescope, time t, you find the position of this meteor, and you chart it, you label it. Now, tomorrow, same time, you look back through your telescope, and again, chart the position of this meteor moving through the sky. So clearly, some time has passed, right, from tonight to tomorrow night, and clearly, the position has changed. So, how do we think about point Q? Well, this is, again, it's a point on the curve. But it's not obvious. I think you'll agree with me. It can't be at time t, because at time t, that meteor was at point P. So some time has passed. So we will say it's a point on the curve at time t plus. Now, this is how much time has passed. I'm going to go ahead and just say delta t. Make sense? So if delta t is 24 hours, then this would be the position 24 hours from now. All right. Okay, so we're getting somewhere. So what we want to do is we want to start to think about what's happening at point P. So if we were only interested in position, right, then we don't really need calculus. But if you start to ask questions like, I wonder how fast that meteor is moving at point P. Well, now you're starting to ask a more advanced question, right? And this is definitely a question for calculus. So how do we get there? Well, you know that if you had 2 points, so for example, P and Q, it's very easy to find the rate of change between 2 points. If you have point P, you have point Q. Well, 2 points is very easy to find the slope, right? The rate of change. Just rise over run. But unfortunately, you asked a more advanced question. You didn't ask what was the rate of change from P to Q, right? That would be, let's just start using velocity. That would be an average velocity. No, no, no. You asked a more advanced question. You asked, what's the velocity at point P? All right, well, let's try to build from there. So right now, P to Q is the distance from P to Q is just some type of secant. What we want to do is we want to find the velocity at P itself. So that distance from P to Q is going to have to decrease, right? It's going to have to get smaller in order for us to find a velocity at P. So how are we going to do that? Well, let's start with R of t. So here's how vector valued functions work. So if you looked through your telescope and at the sky and you plotted that point, there would be some vector that points to that point P on the curve. So R of t maps to point P. All right, now, when you, 24 hours, say, from now, you look back through your telescope and the movement of this particle, this meteor, has changed. It's now at Q. There would also be some vector that would map to point Q. So R of t maps to point P. What vector would map to point Q? Well, that would be R of what? R of t plus delta t. All right, if you are along for this ride so far, if you're still with me, well, first off, hats off, right? But we're almost there. I'm almost to where I need you to be. Okay, so hang in there. Let's now think about slope. All right, now that is when we have 2 points, that's the change in y divided by the change in x, right? Rise over run. Let's write that in terms of the notation we use for vector valued functions. So instead of delta x, it would be delta t, right? So a little bit of time has gone by and the position has changed. And instead of delta y, it would be delta r, the change in r. All right. And now we have everything we need to build this slope formula. So tell me, what is delta? Well, actually, let's start with delta t. That's going to be easy enough. So what is delta t? Well, the change in time, let's think about the change in time. So it would be, the change in time would be t plus delta t minus t. Right? Just like the change in x is x sub 2 minus x sub 1, the change in t would be the t plus delta t minus t. And what does that actually equal? Well, if you drop those parentheses, don't you see how the t's would cancel out? Right, so you're just left with delta t. Simple enough. Now what do we think? How do we think about delta r? So, all right, follow me up here to this graph. So here is r of t, and here is r of t plus delta t. So the change in, r changed. Let's now write it. So y sub 2 minus y sub 1 would be r of t plus delta t minus r of t. Wait a minute. Stop. Look. Have you seen something like that before? Does that look familiar? Don't you remember f of x plus delta x minus f of x over delta x? Wait a minute, that looks like something you've encountered before. And now, all you have to do is, since we don't care about the velocity, the average velocity, right? We want the instantaneous velocity. So if we take the limit as delta t approaches 0, and couple that with this Newton quotient, what do you have? Say it. No one's listening. What do you have? You have a derivative. Exactly. It's exactly right. You have an ability to take the derivative of a vector valued function. And I have very good news. Ready? So dr of dt, so that would be the derivative of r, right? So r prime. Here's the good news. You get to use all the derivative rules that you've already memorized, and all you have to do is take the derivative component by component. So you take the derivative of the I component with respect to t, you take the derivative of the j component with respect to t, and you take the derivative of the h component with respect to t. Maybe you're thinking, well, Professor, why didn't you just get me there a long time ago? Well, that's because you needed to see it, right? If you don't, let me tell you something. If you don't know limits, then you don't know calculus. I don't care how many derivative formulas you memorized. If you don't understand limits, then you don't understand calculus. Ready? So we don't really need to go into too much further for the theory part. Let's jump in and let's take a derivative. Let's go. So we have the following vector valued function. R of t is equal to ti plus t squared plus 2j. This is a multiple part question. First, find the derivative of r, and we also want to evaluate r and r prime at 1. Ready? Let's start with the derivative. So as I said, we get to just go component by component. So what's the derivative? Let's start here with I. What's the derivative of t? Well, that would, just like the derivative of x, dy dx is just 1, the derivative of t would just be 1. I'm going to write it even though it's going to be 1i. And I agree with you. We're going to leave it. Normally you would leave that as just I. But I just want you to see it. This is the first problem. All right? And now let's go to the second component. So the derivative of t squared plus 2, derivative of t squared is obviously 2t. And the derivative of 2 is 0, so it's just 2t in the j direction. Well, that's easy. There's your r prime of t. Now to evaluate it, quite simply, if you allow t to be 1, r of 1, we want to plug 1 into the original function. R prime of 1, we want to plug 1 into the derivative. So r of 1 is going to be equal to I plus, and my apologies, I got it in the wrong spot, don't I? Yep, I do. So r of 1, so yeah, that is, actually I did it right. It's going to be I. And then if you plug 1 squared is 1, plus 2 is 3, so plus 3j. All right, now let's r prime of 1. So again, that's going to be I plus 2j. All right, so congrats, you, at this stage, you can take derivatives of vector valued functions. But what the heck is a derivative of a vector valued function? What, geometrically, what are we doing? All right, I need to see the geometry here in order to understand it. So let's start with r of t. So here is the curve. It's just a parabola. You can see the orientation. We know how to trace it. So that is your curve, r of t. Now r of 1, that is equal to I plus 3j, and you can see the vector coming from the origin pointing to I plus 3j. All right, the derivative. All right, so the derivative is a function, and it's once you evaluate that function, what you get is the slope of a tangent line to that curve. So for all intents and purposes, for moving forward, let's you and I think about r of t as your position function, right? Just s of t. And we can think about r prime of t as your velocity function, and r double prime as your acceleration function, and we can just continue so and forward. But there's two properties of the derivative that make for r prime of t. There's two properties that are extremely important, extremely beneficial. So let me write these cut these properties here. So one of the things that r prime does, obviously it gives the instantaneous rate of change at a point. All right, so it runs tangent to the curve. But the second property is the one that's really important. So the derivative, or the r prime of t, always points in the direction the right word would be the direction of movement. That's a little bit sloppy. The direction of the always points in the direction of motion. Let me just make sure you understand what I'm meaning there. So you can see you see the arrowheads. You see how to trace this curve, right? Notice that, so when you plug 1 into r prime, here's that derivative, and see how it's pointing in the direction of movement, right? It's always telling you which direction you're going to go. All right, so let's go ahead and take a break. I will see you in the next part of this video.